We'll wait for a minute for people
Yeah.
to trickle in. All right, let's get started. Thanks everyone for coming to our last graduation lecture. I'm so excited. My name is Alicia, and I am a volunteer for Delta Analytics. Delta Analytics is a nonprofit seeking to leverage people's data science skill for the welfare of the community. And today this is our part of our Global Teaching Fellows program, and we are happy to have Simret here to present her graduation lecture. And this is our last graduation lectures, and I'm very excited about it. So let me introduce Simret. Simret is a software engineer senior at Ethiopia's Institute of Technology. Her research interest focuses on machine learning accessibility, particularly in developing countries. She's particularly interested in examining the impact of these technologies on underrepresented groups. Her area of interest is in AI and human computer interactions from a technological standpoint. Simra just recently got into a PhD program, and I'm very excited to introduce her. And now the floor is yours, Simret.
Thank you so much, Alicia. Um, Thank you, everyone watching. So I'm going to be presenting my graduation lecture for my Global Teaching Fellowship at Delta Analytics. Um, and my topic is going to be on NLP for spoken Amharic. Um, so throughout this lecture, we're going to be talking about a couple of things today. We're going to talk about the motivation and the data set curated for this particular project. And we're going to focus on speech recognition systems and the features that are important for these type of systems. And we're going to focus on probabilistic NLP for this problem set. And we're going to finally take a look at a code example or a code lab. And we're going to finish up there. So we're going to talk about Amharic. And to give you a little perspective or context on the language, Amharic is one of the Afro-Asiatic languages that is mainly spoken in Ethiopia. It is a very old language. Its oldest artifacts or records date back to the 14th century, and there are songs and poems recorded in this language. Amharic is also the second widely spoken language in Ethiopia, with about 30% of the population using it in their day-to-day lives. And Amharic is written in Ge'ez alphabets. They're also called fidels. And Ge'ez is one of the ancient languages of the world. There are 33 basic consonants or characters in Ge'ez, and each of them have 7 different variations depending on which vowel is associated with them while being pronounced. And Ge'ez is a dying language in Ethiopia. It was once used by everyone in Ethiopia, but today it's only understood and used by a handful of people. But it is important to note that there are a lot of historical, cultural, and religious artifacts written in this language. And one of the most interesting facts that I came across while working in this project is that there are about 7,000 languages spoken around the world today, and only 7 key languages, have been amplified in NLP research. And that is 99% of 99.9% of the languages of the world are not equally represented in research and processes of NLP. So why do we even need NLP for languages like Amharic, specifically for under-resourced and underrepresented languages? One of this is also true for other languages, but studying NLP for Amharic gives us an insight into one of the world's oldest civilization. And because Amharic is born of Ge'ez, it can also be a means to revive and preserve a dying and endangered language like is. Because there's a lot of content being created with this language today, studying NLP for Amharic and a lot of other languages, under-resourced languages, can also give us a data-driven insight into the day-to-day lives of the current societal, political, and economical aspects of people's lives today. And it's studying NLP for under-resourced languages can also give us better accessibility to both literate and illiterate users of different technologies. But there are a lot of challenges faced by NLP in language in Africa and other under-resourced languages. One of the major challenge is that there is not a lot of data available. And because data availability, the quality and quantity of the data available as well is very important in studies like these. And because the data that exists is in more of an analogous form than a digital form, it can be very difficult to organize and analyze these data sets. There's also a lack of benchmarks because benchmarks help us analyze the progress and track the progress being made in a certain field. The lack of benchmarks can create a challenge in doing so. So that is why one of the major tasks that we undertook in this project is trying to curate a data set for the spoken Amharic language. We've tried to incorporate different sources that we thought were important in this corpus, and the major source is children's books, because a lot of the languages that are used in children's books are phonetically rich. We've also tried to use different news sources like Amharic BBC and different open source audiobooks that exist. And through this, by curating this data, we've gotten about an hour and a half worth of speech data set, and we've tried to make this as representative and balanced curation of the data set as possible. And this dataset, this Amharic dataset also follows the power law of large corpuses, and it can be found in the link provided in this slide. So our main focus for today is going to be on speech recognition systems and the features that are important in this aspect. So to give you a little perspective on what speech recognition does, let's take a look at a very high level pipeline of these systems. So how a speech recognition starts is you say something into your phone or a microphone, and we would extract a waveform from the given speech. This is basically changing the analogous form of the sound signal into a digital representation. And then we extract the features and break down the different phonemes that exist in the waveform. And finally, we find the most likely phonemes that could have created or that could have caused the input waveform to occur. So the challenges that we faced for this specific project in Amharic speech recognition is that because the data set had a couple of noises and echoes, it was really hard to handle. And because Amharic is used from in a wide range of the country, there are different dialects that exist for the language. This also created a challenge for Amharic speech recognition. And lastly, I'm sure this is true for other languages, but the contextual relation of words matters specifically in Amharic. For instance, let's look at these two words. The word here can be pronounced as Bella or Bella, depending on which words come before and after this specific word. And it can mean either he ate or speak. So you might have heard me use the term phoneme. A phoneme is a very widely used terminology in speech, in audio, and speech research, and in linguistics as well. So a phoneme it's a very small sound feature. It's the smallest sound feature that creates a contrast in meaning between two words. But a phoneme is really a mental representation of the sound and not a physical representation of it. So, for instance, in this in the two words map and nap, the word map is changed into the word nap by changing the phoneme m into the phoneme n. And same goes for the words tag and tan. The phoneme g is changed into the phoneme n to change these two words in meaning. And so those are different examples of phonemes. Amharic has 7 vowel phonemes and 33 different consonant phonemes. But how we perceive sound as humans or in the physical form is not necessarily how a computer perceives sound. And the digital form, a sound is merely a sound signal, and this is represented by waves. So the features that exist in a sound are represented in the features that exist in a wave in a computer. For instance, the frequency of the sound corresponds or represents the pitch of the sound. That is, the higher the frequency, the higher the pitch is. And the duration of the sound is directly related to the wave's persistence, meaning the longer the persistence or the higher the wave persistence is, the longer the sound we hear is. And intensity is also directly related to the amplitude of the waveform. That is, the higher the amplitude of the waveform, the louder or the more intense the sound we hear is. So let's take a look at these two different waves. So by just looking at these waves, which do you think would create the louder sound? Yes, that is correct. So to see the intensity or the loudness of the sound, we look at the amplitude. And because the amplitude of wave B is higher than the amplitude of wave A, we can deduce that the sound wave B is going to be louder or more intense. So to recap, we said that loudness corresponds to amplitude, and the pitch of the sound that we hear corresponds to the frequency. And this graph you see here, it's a representation of the intensity versus time plot of a waveform. So this plot gives us information about the intensity of time throughout the intensity of the sound throughout time. But that is not all of the information or much of the information that we need from the sound. We also need information about the frequency. And we can get a different kind of representation of speech using the fast Fourier transform. So when we perceive sound, when our brain perceives sounds, what it does is it takes a complex sound wave and it kind of decomposes it into different single frequency waveforms. And we can use the fast Fourier transform algorithm or tool to do this in computers. So what this does is it takes as an input time versus amplitude or a time versus intensity representation of a waveform, and it changes it into a frequency domain waveform. What this means is the representation of our speech changes from looking at how the sound changes, how the intensity of the sound changes over time, to looking at how much of the sound lies within each frequency band over a range of frequency and time. And therefore, this gives us more information about the different frequencies that exists in this particular audio or in this particular speech. But how do we actually get the important audio features for our speech recognition system or any other speech system? So feature extractions from audios is performed by converting the speech waveform to a more parametric representation with minimum data rate. And we can achieve this goal by using the mil frequency substral coefficient, or MFCC for short. MFCC is one of the most important feature extractions that is being used in speech recognition. So in our pipeline that we introduced previously, the MFCC or the feature extraction would occur here. So the MFCC it's a simulation of the human hearing system. It aims to replicate how our ear actually works artificially. And it also takes into consideration the different perception of sensitivity of the human ear. And that is why we deem this tool suitable for speech recognition tasks, because it helps us understand the different frequencies at which humans speak or utter. And we use the logarithmic scale because there is a huge range of difference between the smallest sound we can hear as humans and the largest sound we can hear, so much so that it would tear our eardrums away. And this range can reach up to quadrillions, that is 1 followed by 15 zeros afterwards. And because this range is a huge number, we use the logarithmic scale to better manage it. We use the MFCC for speech recognition because it's been tested in a wide range of applications, and it has proven to be very efficient and important sound feature. But because MFCC also gives us less number of features, it's more efficient and easier to manage in our systems or to train in our models. MFCC also has a good error reduction, and it helps us produce a robust feature extraction for signals that are affected by noise. And because MFCC is a replication of the human hearing system, it is more intuitive to understand for us. The intensity at which the sounds exist is more intuitive. So our focus for today is going to be probabilistic NLP. Revisiting our pipeline from earlier, we said that the final step is we try to find the most likely phonemes that might have created the waveform presented. The keyword here being the most likely, meaning that the ones that have high probabilities. That is where probabilistic NLP comes in. So in this section, we're going to break it down into a couple of subsections. We're going to talk about hidden Markov models, but firstly, we're going to talk about Markov chains because hidden Markov models are basically made up of discrete Markov chains. And we're going to talk about the Viterbi algorithm for the decoding problem. So the objective in the context of speech recognition is to find the most likely sequence of words that would give us the acoustic input or the audio input. And the strength of hidden Markov models is because they are a mathematical framework for solving sequential data, and because speech has a sequential pattern to it, they can be very efficient and important in this aspect. So we have the audio features or the acoustic input, acoustic features as our input, and we have the words as an output. So this is the infamous speech recognition example. So we have two phrases: recognize speech and recognize speech. These two phrases are basically made up of very similar phonemes, and they kind of could sound the same, but we would want our hidden Markov models or our speech models to distinguish between those two very similar sounding phrases. And probability here makes it possible for our model to differentiate between very similar sounding phrases or words. So the goal is to reconstruct the words that are being said or uttered by reconstructing the most probable phonemes using statistical probability. So how this would work is that we would present the MFCC extracted audio features to our hidden Markov model, and our hidden Markov model would give us an estimation of probability of different phonemes or phrases or words, and would decode and recognize our phrases or words. So to give a very formal definition of hidden Markov models, hidden Markov models are graphical probabilistic models that allow us to predict hidden variables or unknown variables from observed variables. So a hidden Markov model is basically composes two types of variables. They can be hidden or observed. We know every information about our observed variables, and we have no information about our hidden variables. So in this real life scenario, let's say that you are in a windowless cafe. It sounds very miserable, but let's say that you're in a windowless cafe and you can only tell the weather outside by looking at what accessories people walking into the cafe are holding. People can be holding their umbrellas, sunglasses, scarves, and so on. In this specific scenario, we can say that the hidden variables or the observed variables in this scenario are the people's accessories or what they carry, and because we have every information about this, we can see the people coming into the cafe and what they're holding. And our hidden variables or our hidden sequence would be the weather outside, because we have no information about the weather outside, but we can predict the weather outside using our observed variables, people's accessories. And in speech recognition context, we know what the audio signals being emitted are beforehand, but what we don't know is the actual words being said or uttered by the speaker. So in this context, which do you think is the hidden state? Yeah, that is correct. Yeah, because we have no information about the other words, or we don't know what the words are beforehand, we can say that our hidden variables or our hidden states are the words or phrases being said or uttered, and our observed variables or our observed sequences would be the features that we extract from our audio. So to recap, this is a visual representation of a hidden Markov model, and the nodes or states at the bottom represent the hidden state, that is the phonemes that exist or the words that are being said, and the observed variables represent the audio signals or the features we've extracted from our audio signal. So hidden Markov models are basically made up of Markov chains. Markov chains describe a sequence of possible events and states, and Markov chains describe basically different states and their transitions. So in this specific example, we are trying to represent 3 words made up of 6 different phonemes. And if we take this particular path, we're representing the word gap. If we take this particular path, we're representing the word no. And if we take this particular path, we're representing the word go. And Markov chains are useful when we need to compute probability for a sequence of observable events. For instance, in this example, we can see that the probability of getting the phoneme e, given that the previous phoneme is n, is 0.7, and the probability of getting the phoneme e, given that the previous phoneme is g, is 0.2. But in a lot of real-world problems, we are not always interested in what we can observe. Sometimes we might want to know or to get intuition about what's hidden from us. And that is where hidden Markov models shine. So hidden Markov models give us two layers of information, the hidden variables, and are graphically represented by Markov chains, and the observed variables are the features we've extracted. And hidden Markov models contain all possible states of the system and all possible transitions or probability of transitioning from one state to another. This information is saved in the transition matrix. So in the transition matrix, the rows represent the current state that we have, and the columns represent the next state that we might go to, or the probability of going to the particular next state. Hidden Markov models also contain emission probabilities. This represents the probability of seeing certain observed variables given the value of a hidden state. And in this particular matrix, the rows represent hidden variables or hidden sequences, and the columns represent the observed variables. So let's take an example here. To recap, we said that a transition matrix holds information about every state and the possibility of transitioning from one state to another state. And the rows are representation of the current state, and the columns are representation of the next state. So this particular question states, what is the probability that the next phoneme is I, given that the current phoneme is G? Yeah, that is correct. So to get this particular probability, we take the current phoneme, that is G, we'd go to the row, and the next phoneme is I, and where they connect is the probability of transitioning from the phoneme G to the phoneme I. So a hidden Markov model is basically contains a couple of things. That is the transition matrix containing information about every state and their transitions, the observation or probability matrix, or the emission probability matrix, that is containing information about the observed variables and the hidden variables, and the initial distribution matrix containing the initial distribution of our data. And a hidden Markov model tries to answer three basic problems. That is the evaluation problem, the decoding problem, and the learning problem. The evaluation problem tries to answer is basically finding the probability of observations given the model. And it tries to answer questions like, what is the probability of this particular waveform occurring in our model? And this can be important if we're trying to choose among several competing models. And the solution here would allow us to choose the model that best fits or matches our observations. And there is also the learning problem. The learning problem tries to adjust the different parameters that exist in our model to maximize the probability of the observations given the model. And the decoding problem, in this problem, we try to attempt to, or uncover the hidden parts of the model. What we require here is to find the best states or sequences for our observed variables, or a suboptimal solution here. So this problem tries to answer questions like, what is the probability that this following waveform was produced by the phonemes that exist in no? And we're particularly interested in this problem, or the decoding problem, because speech recognition basically tries to answer questions like this. There's a lot of ways of answering this question, and we can try. One of the solutions can be maybe finding all combination of phonemes that exist in our corpus and trying to find the probability of each combination, and maybe choosing the one combination that has the highest probability. But this is not efficient or optimal, because the number of states in our model would exponentially increase as our corpus gets bigger. And that is why we use the Viterbi algorithm. The Viterbi algorithm is one of the widely used algorithms in the decoding problem. And we use this algorithm to answer the decoding problem. So the Viterbi algorithm tries to determine which hidden sequence is the underlying source of some observed state. So here the goal is to find the audio. So the goal here is, given some audio feature, to find the most probable cause of this audio feature, this audio. And what the Viterbi algorithm tries to do, or the idea behind it, is it trails the observation sequence left to right, and it tries to get rid of every path that goes to a particular to a specific node, except for the one that has the higher probability. For instance, in this particular very small Hidden Markov model, we can see that two paths can lead to the phoneme. The first path we can take the path n to eventually spell the word no, which has the probability of 0.7. This path has the probability of 0.7. Or we can take the path g and then to spell the word, to pronounce the word go, which has a probability of 0.2. And because the probability of the first path is bigger than the probability of the second path, our algorithm would pick this path and completely disregard the second path. So we can take a quick minute to take a look at a code walkthrough. So in this specific code lab, we tried to create a hidden Markov model, or specifically a Gaussian hidden Markov model, using HMM-Learn. And we used LibreOS's MFCC feature extraction to get the features for this audio. We're using our corpus that can be found in this GitHub link. And after getting the corpus here, we try to create the speech list, and we try to extract we try to extract the male frequency substral coefficients using the LibreOS feature extraction library here. And after that, we train our models, our hidden Markov models, using the training dataset that we've imported from GitHub. After training the dataset, we've tried to get a test dataset here, and we've randomly chosen the first speech list from the first speech list, and it's unmissed, or the number 5. And so we try. So to give an overview of our hidden Markov model, what it looks like is we're using the Gaussian hidden Markov model or the Gaussian mixture hidden Markov model. And for the decoding algorithm, we're using the Viterbi algorithm. And so we would look at our predictions, and finally, the prediction that has the highest probability would be our final prediction or our word prediction, which spells a mist or the number 5. So the next steps, it's been really fun working on building this Amharic corpus, and it has been very interesting as well, starting from getting the noisy neighbors to keep it down while recording to running different experiments on the dataset at hand. And moving forward, we would like to incorporate more representation in the speakers of the dataset. We want the dataset to be representative across different ages and genders. We also want to go on building the corpus to make it phonetically rich, because Amharic is one of the most phonetically rich languages out there. And with that in mind, we would love to keep working on crowdsourcing the different data sets and creating a platform for different people to make a contribution to this corpus. And it would also be very cool to run different experiments on on our collected corpus using different algorithms like deep learning. I'd really like to thank everyone at Delta Analytics and everyone for coming to my talk today. And I would very much like to give a special thank you to Alicia, my mentor, for helping me come up with this presentation and putting in a lot of hours in helping me achieve this. If you have any questions, I'd be happy to answer them. And please get in touch.
Thank you, Simret. This is such a good presentation.
Thank you so much, Alicia.
So we have a question. So the first question is, what are next steps for you or for this project?
So for this project, I feel like there is a lot more corpus to create, or a lot more data to collect, and I'd like to keep working on that.
And is there, as a follow-up question, is there a particular type of corpus or particular data sources that you are looking into currently?
Yeah, so originally my idea was to go with text-to-speech synthesis, and I was very interested in that project because I thought that it would be very important the in the education system here in Ethiopia, because there is not a lot of teachers creating a text-to-speech system that would help students learn how to read would be very helpful in that regard. And so one of my main focuses was trying to use children's books to create a data set of children's books speech that would teach children how to read.
Great. Yeah, this is a very unique corpus, and I think it's a great start. And if there are no questions, I wanted to follow up on you're starting a PhD very soon. Is there any research focus? Will your research focus be the same, or do you want to enter into a new field?
I'm actually going to be entering into human AI collaboration in the HCI field, and I chose this, or I'm interested in this field because a lot of the technologies or the solutions that are created don't necessarily put into context the lives of people in the underrepresented places or countries like Ethiopia. And I would very much like to study the impact of those solutions in societies like mine, and what different alternative of solutions would better be helpful.
Great. Yeah, this is definitely a great area to enter into. We have a new question from Cynthia. She said, well done. And what institute are you thinking of working with to build out the corpus in addition to school?
Oh, so for the collection of data?
I think, yes.
Yeah, so in the main form of media outlets for a couple of years in Ethiopia was the radio. And there was this children's show called የልጆች ጊዜ in Ethiopia. And it basically has a lot of data, or it's a mine of data set that exists in some shelf, probably in the Ethiopian Broadcasting Corporation. And I feel like that would be a very helpful data mine or data sets to look into. That is my next focus.
All right, we have some appreciation from Alasan. Your lecture was great, Simret.
Thank you so
And we
much.
also have appreciation from Delta Shuttle, which I think it's Melissa, plus 100. Yay. Okay. So thanks everyone for coming to our last graduation lecture. And this is the end of our public lecture for this year. Please stay tuned for our Global Teaching Fellows cohort next year. We will come back soon with more great contents in the future. And thank you, everyone.
Thank you so much for coming. Thank you, Cynthia.